And then there are a couple visualization tools that we can use to kind of step through these things and see what's going on where. So we'll do some of that as well. Computer. Oops. My computer just gets non-responsive. Okay. But before we start with that, assuming that we're just going to jump into that thread on the help channel, Marshall, any other questions about stuff that's come up or observations that you noticed yesterday about any of the pointer things that caught you off guard or otherwise? Did you find that the pointers were the hard part and the rest of it was pretty straightforward, or were there other things besides pointers that were tricky? Pointers mostly. So for those of you coming from the JavaScript world, I will point out that you have effectively used pointers before in JavaScript. You just didn't have to deal with the minutia associated with it. So you might remember that in JavaScript, if you pass an object to a function and you change that object inside the function, that those changes will be reflected back in the caller, which is different than the little experiment we did yesterday where we passed integers into a function and we changed those integers and we noticed that those changes were not reflected out in the caller. But when you pass objects in JavaScript in, the changes are. What this means is that JavaScript is passing those objects by reference. It's actually using a pointer to pass objects into functions. The only difference is you don't have to use ampersands and asterisks. It figures that out automatically for you. Returning values when it's referenced for and dereferenced, yes. Let's start with that thread. Let me dig it up. It was this thread here, which is awesome. So I'm going to throw this into a couple different visualizers, and we'll step through it and see what happens. This one I was just introduced to today, so let's see if I can make it work right. So the idea here is that we want to take the string hello and we're going to copy it into this buffer. And here's the code for string copy to make that happen. So I'm not sharing my screen. I owe you a quarter. Yes, yes, yes. All right, let's make this happen right. Yep, it's going to be your thread. Because this has a lot of great examples in it. So if let's see, I said execute this, and I'm going to say step into and so on. And down here at the bottom, I want to describe what we have here. Let's see if I can make this appear bigger marginally. So what we have at the bottom here is representation of memory. Remember that I said yesterday memory is basically a big array, and that's what we're showing here at the bottom. The numbers above the array, these are the indexes into the array. Remember, the index into memory is also a pointer. It's also called a memory address. So these top numbers are the indexes. They're in hexadecimal, which we haven't really talked about yet, but just assume they're numbers. And FFFF is our biggest number in this example. The values in the boxes, this is what's stored in the array. So far it's just full of zeros. memory's got nothing in it. So let's step through and see what happens. I haven't actually stepped through this one yet, so it'll be an adventure. Let's see. Step over. That's fine. So we've initialized some things here. I've got this area right here. This is our buffer. And it's full of zeros, which are the same as the terminators for strings. That's what it's showing us here. And we also have a pointer hello here, which is currently pointing at address 100 hex. If I jump back this way, we should get to 100 hex. So here we are at address 100 hex. It's highlighted. I see there's a 48 in there, followed by 65, followed by 6C, followed by 6C, followed by 6F. All hexadecimal numbers. And these are all the ASCII representations of the word hello. So 48 is H, 65 is E, 6C is L, 6C is L, 6F is O. And then there's a null terminator here at the end, 0. So that's our string hello stored in memory. And the buffer itself is way up here at address FFF2. So something interesting to note and potentially confusing is that the value of the pointer hello is 100 hex. So that's the value of the pointer. If we pop back here, it's actually 100 hex is the index into memory that we're interested in. That's where hello is stored. So that's why hello is a pointer. Its value is the address of a thing. So hello doesn't store the word hello in it. The hello variable does not store the word hello in it. All it does is have the address of the first letter in it. That's all. I see Jonathan typing. We haven't actually gotten to the string copy yet, but we're almost there. Jonathan, that's a great question. Is \0 stored differently from 0, or is it just interpreted as a null terminator? So it turns out it is actually 0. So \0 is a numeric 0. It's just 8 bits long. It's a byte, or put another way, it's a char type, as opposed to an int type. But its numeric value is 0. So, well, conceivably, you could null terminate your string by just saying that pointer equals 0. That totally works. It's slightly more correct to use the \0 version, because that specifically is a character, but technically equivalent. Andrew, your question, is there a way to convert hello to hello? It's, I'm not sure I'm answering that question here, but it's this. Is that what you're asking, or is the question different? Those two things are exactly identical. To the point of the first element of hello, of the string hello. So this is a tricky question to answer. because of this equivalency, the fact is there actually aren't any. The concept of an array is a nebulous one in C. It's basically, when we talk about a C or an array in C, we're talking about a pointer to the first element in the array. There's not really much of a difference between those two things. Size of actually works on everything. But using that gets you the size of the pointer. Yeah. Let's run this example, and then I can actually show you how that works. So you're touching on something that in C I would call array pointer equivalence, and yeah, we can look at that. And the weird part is right here, right? Let me edit this code. Let's start again. Edit. The weird part is right here. Size buffer. Actually, if you're using a variable, you don't need the parentheses there. It's only if you have a type in there you need the parentheses. So input out terminal, we should see that. Size of buffer, and then we pass buffer in right here to string copy, where it becomes char pointer x, right? So we'll step through and see what happens here. So we got hello in the buffer. We're going to print out the size, which output terminal. There we go, 10. All right, so we printed out the size of the buffer. It said it was 10 bytes long, which makes sense because it's an array of 10, right? Now let's jump into here, and then I'm going to print it out again. Buffer became x here, but now it's a char pointer, and it says the size of x is 4, which is kind of weird because down here it was a buffer, and up here it's a pointer. We could actually change this if we wanted. If I click edit, hang on a second. Let's change this to an array of 10. This is the freaky bit. I'm even getting a warning on it right here. But let's ignore that warning for a second. We'll jump back to it. I'll step through. We print out the size of buffer, which prints out 10. And then we come up here and we're going to print out the size of x, which we've now made an array of 10, right? Printed 10. I totally did not expect that. That is freaky. Hang on one second. This is destroying my demo. So I just tried this yesterday. Yeah. Let me try one more thing. This is a different result than I get on my compiler on my computer here. So it's destroying my demo. One more time. All right, so I'm going to have to demo this on my computer because this compiler and interpreter is messing it up for me. Let me bring this up for you guys. I change this into an array of 20. All right, so here's the demo that I wanted to give. And I'm just going to blame it on the weird interpreter doing the wrong thing. So I compile this program, and it says, I'm missing that thing. Let's add that. Sometimes replit style interpreters do strange things. All right, so when I compile this, I get a warning saying that the size of the array parameter will be the size of a char pointer instead of char 20. So it's warning me right here saying that despite the fact that you declared this thing as char 20 in foo.c, or in the foo function, string compare function, it will return the size of char instead. So if I run this, sure enough, it tells me that. It says that the size of the buffer is 20 bytes, but the size of x is only 8 bytes, which is really weird because clearly I've said it's a 20 byte character array here. So why is it telling me it's 8 bytes? So the answer here is that C does something behind your back. Whenever you refer to an array like this by its name without any brackets afterwards, this is exactly like saying the address of buffer 0. So this line right here, this is exactly as if we typed this thing right here. So these two lines being equivalent, what we have here, since we've taken the address of, is we've definitely made a pointer out of this thing. And so this becomes a pointer up here. It turns out that C is a little forgiving. If we want to declare our function to be an array like this, it's like, fine, you can do that, go for it. But the compiler just pretends that we had typed this instead. In fact, it doesn't even matter what the number is here. In fact, it doesn't even need a number. These lines are equivalent. If you put anything out here, the compiler is going to just change it into this thing and be done with it. So as such, there's no way to pass an array, like pass all 20 bytes of that array into a function. The only thing you can do is pass a pointer to the first byte of it. I don't know if that's clarifying at all. It's one of those esoteric C rules that you just commit to memory and you're like, yep, that's what happens. This array inside the function signature gets changed into a pointer. And there's simply no way around it. Marshall, exactly. When you get the point of the first item, you just go up by 1 to get to the second item, and so on. As for why this little environment here was printing out 10 for the size of the array, I'm not sure. It was even warning me that it wasn't going to do that. That size of was going to return the size of char pointer, but then it didn't. I don't know. Let's switch this back to what it was. Char pointer X, and I'll make this 10 again. This line right here, this is a comment that is controlling this environment, so you can ignore that line. All right, so let's see. Step into this stuff again. The size of my buffer. This time, hello is actually, the address is slightly different. It's at address 113 hex. That's okay. It might vary from run to run. If we pop down to address 113, I said 113? Yeah. Oops, I need to go this way. No, I don't. I need to do this. What do I need to do? It's unfortunate that it's at 113. I'm going to take out this printf and see if that moves it back. No, stop. Oh, boo. So when I'm recording the screen, the mouse is super sluggish, and it's really easy for me to click in the wrong place. And now that I've clicked over here, it's done me the favor of removing all that code conveniently. Nope. Try again. Sorry, gang. Technical difficulties. Nothing like a live demo. Ah. Okay. What do we have? We have a bunch of stuff. I've just stepped into the function. So we've got our buffer starting at FFF2. And we've got our string hello, which starts at address 10E, which I can now hopefully see. 10E right here. Starts 48, 65, and so on. So one touchy slider. So what are we going to actually copy here? Start that size of. We've got an integer z. We see the z is right here in memory. We see these things barely labeled. This one on the left is z, then y, then x. And z currently has the value of 0. We're going to go into a for loop here, though. And we're going to check all this stuff out. So what are we doing? We've got z is 0. We're checking out y sub 0, which is the 0th element that y points to because of that equivalency that we have right here. So it's the 0th element. We're checking basically to see if it's true or false, if we're at the null terminator or not. And then we're going to add 1 to z, and then we're going to do an assignment. So we're not at the null terminator yet because y is pointing at the h in hello. And then we're going to do this assignment. We're going to copy y sub 0 into x sub 0. And there we've just done it right here. It's made the copy. So what happened there? X is pointing at our buffer. We see that right here. X has FFF2 in it, which is the address of the buffer. And Y has 10E in it, which is the address of H in hello. And so we've just copied what was at Y0 into what's at X0. And that gave us an H. So we'll do the same thing again. We're going to increment Z to 1. So we see Z becomes 1 right here. And we're going to test to see if Y sub 1, the E in hello, is null. It's not. So we're going to do another copy. We're going to copy from Y sub 1 to X sub 1 and copy the E right in here. They turn out to be exactly the same, Andrew. You can put 0 there. It's just that the type of 0 is an integer, whereas the type of \0 is a char. So it's nice to have the types the same, and technically they should be the same on different sides of the equals, but C has another concept called like the standard integer type promotions. I don't really want to get into it, but you can effectively treat them equivalently for that purpose. Just in general, whenever you can, make the two sides of an equal sign the same type is kind of the rule. Yeah. Exactly. If you had an array of ints and you just had an arbitrary 0 in the middle of that array and you were scanning until you got to a 0, then it would stop scanning at that point, right? So usually with an array, people pass a length along with it. It's really nice in JavaScript or Swift or other modern languages when you have an array, you're just like, what's the length of that array? But in C, if you pass an array to a function, as we saw, it just gets pointed to the first element. The length is not something that's even in there. So usually in C, when you're passing arrays around that aren't terminated in some way, like strings have the null terminator at the end, if you're passing them around without a terminator, then invariably a length gets passed around with them as well. You'll see a lot of functions in the C library that are like, hey, I want to print out this many bytes of this thing, or I want to process this many bytes or this many elements out of the array. And you'll also actually see a lot of null terminated arrays out there too. So if you have an array of pointers, for example, then maybe the last pointer is null. And that's how that array is terminated. But those are basically your two options for dealing with arrays in C. You either put some kind of terminator at the very end that you'll recognize when you're looping through it, or else you pass a length. So on this part of the program, so far so good. It looks like we're incrementing Z and we're copying hello. And then we quit once the string is copied. Look at that. It actually copied hello, and it's got a null at the end even. So it looks like, in this case, it worked. But it did not pass the test. And the reason it didn't pass the test, well, let me ask, does anybody see the reason why it might not have passed the test? It looks like in this case, when we ran it, it looks like it would pass the test. That's the word hello, all right? So let me restart this thing. Let's look at what gets copied. H, E, L, L, O, and that's all. But what do strings have to end with? It's a null character. We didn't process the null. We got lucky. There happened to be a null in memory right here on this run. So it worked this time, but on somebody else's computer or on your computer on a different run, maybe this isn't null. Memory isn't necessarily initialized to anything in particular. It could just have garbage in it. So if this weren't null, if this happened to be the letter X out here, then it wouldn't have worked properly. Let's do a quick change to this code where we actually initialize the array to have a value in it. So I'm going to initialize this to be, I don't know, let's make it a bunch of 5s. There we go. So now the array will have a bunch of 5s in it. And we'll step through. We see them all here. We got 5s, which aren't any character. It's an unprintable character. They're not an ASCII character, I should say. And so now we run through and we make our copy, LLO, and we're done. So here the string is bad because we happen to have something that wasn't nulls in our original buffer. So we've got to copy that null terminator around. So we can do one more thing. Let's see, Z points at the end of it right now. X is the destination. So we can do some kind of null terminator like this. At the very end of it. I'm hoping that that HELLO, and then we're done. And then we put a null terminator on. And now we're really done. And I think that was what was missing from that one. This is one of the insidious things about C. We just ran it and it was fine. But then you ran it earlier, Marshall, and it said it was failing the test. somebody else might have taken that same code and run it and had it work just fine. We are, by not null terminating that string, we are potentially engaging in something called undefined behavior in C. If somebody goes to print the string out and there's no null terminator at the end, it might very well print out past the end of memory that was allocated for that string, resulting in a buffer overrun. And if you do that, then you enter the world of what C programmers call undefined behavior. If you access elements outside of an array, then that's what happens. And once undefined behavior occurs, anything can happen in the run at that point. Could run fine, could produce weird results, it could crash. So that is one of the main things that modern languages try to get away from. It's like, here we've made an error, a really easy error to make, and the result worked out just fine. Sometimes, and it's exactly the sort of thing that would work out fine when you're testing, and then you go roll it out in production and it breaks. And developers got tired of that happening. And it's not that people are bad developers, it's just that we're only human and programming is hard. So modern languages come out that avoid problems like this. If you want to copy a string in JavaScript or in Swift, there's like no chance it's not going to be terminated correctly or the length won't be correct because you're using some library in the function or in the language that's totally takes care of everything for you. You don't even have to think twice about it. C does us no favors. This is absolutely true. So there's also, I want to run one more visualizer. You can also go to Python Tutor, C version. Yeah. Let me run this program. Oops. I forgot to null terminate that thing. So it might not actually, no, it should run. Main server is busy. Oh, here we go. All right. So this visualizer is a little bit different. We got our code on the left. We have some stuff on the right. We got hello, which is a pointer to who knows what yet. And we got a buffer that's full of unknown stuff. So here we've just initialized hello to point to this string hello with a null terminator. And then we're going to jump into string copy. And we see we have local variables x, y, and z in here. X is a pointer to the buffer. Y is a pointer to hello. Z is currently unknown because we haven't initialized it. But now Z is 0, and we do a copy. So we see the H gets copied, and then Z becomes 1, and the E, and so on. And then we're done. In this version, I have not null terminated the string. So we see that we have hello, but we haven't copied the null terminator. So I don't know which visualization works better for you guys, but I can put out links to both of them. I do want to point out one more thing in this visualization here. Let's see, what are we doing? We've just gotten out of the function, so we're here at the end of main right now. Right here, this value at the end, this hex 10e, that's hello. That's the pointer hello. As we see up here, it has that value. So this is kind of interesting. This might be a slightly mind-blowing moment. Hello is a pointer to 10e, but a hello is also just a variable. Like the value of the pointer, which is hex 10e, has to be stored somewhere, and it's stored in memory right here. Hello is a pointer. It's just, remember, a pointer is an index into memory. So the value of the pointer is an index into memory. So here's our pointer hello. This is its value 10e. You can even see the in-memory representation in bytes of what 10e looks like. 000010, So if you can have pointers to variables and a pointer is a variable, can you have a pointer to a pointer? You certainly can. If we were to take the address of hello, that would give us a pointer to the variable hello, which would be kind of weird, but let's not think about that too much right now. I'm going to do one more on these. Well, at least one more. Let me edit this. So this was another attempt, which is very similar to what we had, but let's step through, whoops. Let's step through it and see what happens. We got a warning. Expression which evaluates to 0 treated as a null pointer. Anytime you get a warning in C, you should fix that warning. The warning should not be taken as a hint that something should be different. It's almost always it's a thing that's broken that needs fixing. So we do have a warning there, but let's see what happens when we step into here. We've got hello in our buffer. We're going to call string copy. We're going to do our regular old, oops, what happened here? C equals 0, y, oh, no, we just haven't gone far enough. I also made this bigger so I can't see it. So here we're doing a regular copy, H, E, L, L, and O, and then we stop, and then we set X to be 0. So X is a pointer right now. It points to this slot right after hello in our new buffer, I think. No, wait, it doesn't. Sorry. It points to FFF2. So it points to the H. It points to the start of the buffer, right? We passed in the buffer. And so X is a pointer to the first thing. We haven't actually changed X anywhere. So X still points at the H in our buffer right here. And X is a pointer. And you can set pointers to null, which is a special value that means point to nothing. Null has a value of 0. And so what the compilers warned us about right here is it's like, hey, you gave me a char value right here, which is 0. But on this side, I've got a pointer to a char. So that's kind of weird, it's telling us. And it's saying, I'm just assuming that you type this, but I'm assuming that you mean this, which is numerically equivalent. So that's what that warning was all about. So the compilers assumed that we did this. We'll do our run again, H-E-L-L-O, and then we're done. And so at this point, it's just saying, oh, well, we wanted to set X to null. So X right now is pointing at the H in our buffer. We set X to null. And now X is pointing at nothing, and our function is over. But we still haven't null terminated anything. So that's kind of what happened here. We didn't want to set the pointer to nothing. We wanted to set what the pointer points at to null. So if you have a pointer and you want to change the thing that the pointer is pointing at, what do we have to do? X is a pointer. We want to change what it points at. We have to dereference that guy. So this would make it work. And again, with the pointer array equivalency, that line is exactly the same as this, because adding 0 does nothing. And that line is exactly the same as this, which is the solution that we had earlier. All 3 of these lines are equivalent. So we had this guy before, that works. That's equivalent to this, which also works. Let's see, same thing. Then we've got this. And this one did work. Let's use the other visualizer for this one. Let's see, edit this code. Because this one moves, this one bumps the pointers around. While dereference Y, I'm going to flesh this out a little bit. This is totally fine. And historically, C programmers have done this a lot. 0 is false in C, 1 is true. And the \0 character, that's numerically 0, which means it's also false. So this is basically saying, well, dereference Y is not equal to this. So I'll just flesh it out like that. What you have isn't wrong. It's just equivalent to this. And I find this one to be a little bit more clear. So let's give this a shot. What we're using here at Python Tutor, this is called a time travel debugger, because it shows you values of things and allows you to travel back in time in the run, which is kind of neat. So let's do our thing again here. We're going to call string copy. We've got X and Y, which are both character pointers. We've got hello is pointing at this. X and Y don't point to anything yet. Let's step forward so they get initialized. X is pointing at the beginning of our buffer, so X is the destination. Y is pointing at the beginning of the array, so it's the source. And we check to see if Y points at a null character. It does not. So we come here and we want to copy the value at the address Y is pointing into the value at the address X is pointing to. So we're going to copy the value from where Y is pointing into the value where X is pointing. So that should copy our H over. And now we do some pointer arithmetic. X++ and Y++. This means go to the next character in memory. We know it means go to the next character because the types of the pointers are character types. So if we do this, X is going to bump up from where it's pointing now to the next memory address. And if we do that with Y, Y is going to bump up from the H to the E. So this is kind of interesting. We've got hello is pointing to this, hello, the entire word. Y is pointing to the E, which means that it's technically pointing to a string. That is the word hello, because string is just a pointer with a null terminator at the end somewhere. We check to see if dereference Y is null. It's not. We do the copy again. So that gets us the E over. And then we bump X to the next location and Y to the next location. And so we do this a few more times, copying one character at a time and moving the pointers. There's our hello. And now if we look at Y, we see that Y is pointing at the null character. So we're done. So we step. The last thing we need to do, just like before, we have to put a null terminator on our destination string because there's not one there yet. But X is pointing exactly where we want it. So we say the thing that X points at should be set to the null character. So that does that right there. And that's it. So one of the previous solution was an array notation solution where I used a for loop, which is totally fine. And this one was a pointer arithmetic solution. Yeah, This is, if you mean by lower level, like, yeah, this is low level arrays. We'll call it that. It's in a higher level language, arrays would give you all kinds of protection. You couldn't access stuff out of bounds and cause a crash, or you couldn't access stuff out of bounds and get undefined behavior. It keeps track of the length for you, stuff like that. But at a low level in the computer, this is what we get, which is kind of bare bones. And people are like, okay, well, that was a pain to use, so let's invent a higher level language that makes this better. You could also write your own array stuff in C. You could write a library that had arrays in it, and if you use your functions, you could have your functions checked to make sure that you were within the length of the array and all that other stuff. So it's possible to write higher level constructs that give you that additional protection. It's just that C programmers don't usually do that. They're like, well, if you want that, you should use a different language. Either that, or in the early days, it wasn't worth it because computers weren't that fast, and you didn't want to do like extra checks. Every time you access an array element, you didn't want to check to see if you were in bounds. It would take way too long. You just had to be a good programmer and not mess it up. Let's see. Doesn't this mean that, I like this question, doesn't this mean that pointer X is now pointing at null instead of the H you needed to point it to? Well, let me follow that up with a question. Why do we need X to point to H? This is a great question. I love it. So we definitely need something to point to the H. Otherwise, we've lost our string, right? But the secret here is that we don't actually need X to point to it. But we need something to point to it. Luckily, we have something. We have the pointer hello back here. Pointer hello still points at the H. So when we step out of our function string copy back into main, X, Y, these are gone now. These were just local variables to that function. They're toast. So I step back. So leaving X pointing to the end of the string here, not really that big of a deal. Because string copy is over, its job is done. X is going to go away in a second. I don't really care at this point where it is. What's important is that char pointer hello, we still have that. And we always had that. So hello points at the H. Is that answering the question? Oh, yeah, okay. Same concept. Yes. We definitely lost these pointers. I mean, if I step way back here, like we're corrupting them right away, right? X and Y, they start where we'd expect at the beginnings of the string and the buffer. But as we go along, we're like moving them all over the place. So we're losing the reference to the beginning of the string and the buffer from X and Y's perspective. But we still have the references back out in main for hello that points at the beginning of this string and buffer that points at the beginning of our buffer. Oh boy, Andrew, how this is the rabbit hole. You are peering directly into the rabbit hole, my friend. This question is also fantastic. Remember yesterday how I wrote the first version of add 10 and it was not changing the value out in main because there was a copy of the variable that was passed in? Is that ringing a bell? Andrew? So it turns out that everything in C is a copy when you call a function. So what we've done here, if I go to the first, I'll jump back to the beginning. We have hello that points to this string. We've got buffer that's got these bytes in it. When we call string copy with buffer and hello, we get copies of these two things. They're both pointers. We get copies of the pointers. So X becomes a copy of a pointer to the first buffer element, and Y becomes a copy of the pointer to the H in hello. So every time you call a function in C, the arguments get made into copies. And that's why they appear twice here. This is why in string copy, we've got X and Y that point here and here. And out in main, we've got hello that points here and buffer that's here. So hello and buffer don't actually change because we've made copies of those pointers. So when we change our copies, hello and buffer don't go anywhere. You see X and Y moving around, but hello and buffer don't change their addresses at all. So it's not hello and buffer that we're really passing by reference. It's what they point at that we are passing by reference. That sounds like a not so subtle suggestion, Michelle. Yes, it would be a good time for a break. I'm gonna before we break, I want to throw something out there, um, tying on to Andrew's question there. And if this question makes things too confusing, then just ignore it. But it's a bit of an aha moment. So my question is this: uh, here we saw that what we were passing by reference wasn't the pointer, hello and buffer, but it was what they pointed at. And so by changing X and Y, we're just changing our local X and Y here in string copy. We're not changing hello and buffer, what they point at all. And we can see that hello always points at the H and buffer always points at the first element of the array here. So great. Well, let's say I wanted to write a function that actually did change the pointer. So I wanted like the value hello, I wanted it to change to point to something different, not just the H. In that case, we would have to pass a pointer to the pointer. Because when you pass by reference, you're allowed to change the thing that's being pointed to. But that's an example where a pointer to a pointer would be useful. If you want to have a pointer to a thing and change the value, change what that pointer points to, the address that the pointer points to, then you'll need a pointer to a pointer. Anyway, like I said, if you don't want to think about that, don't think about that. Okay, let's do a break. And when we come back, more pointer stuff? I'm not sure. During break, think about what you want to talk about and we'll direct it that way. But I do have more pointer examples I can give. And with pointers, usually it's just practice and examples before it all starts clicking. All right, gang, where's my timer? Catch you guys in 5. Grab that coffee. Everybody coffeed up? They've all ghosted. How are we feeling? I've got several more examples running through my brain here to step through. I want to write a slightly different set of functions here that I'm going to use a different type. We've been doing all these strings, but we'll do something with an int array. How about? So I want to write a function that takes an array of numbers and say multiplies all the numbers in that array by 2. So let's have, I'll call my int array A and give it a length here, 5. I'm going to initialize that array to have some values in it. And I want to write a function that multiplies an array by 2, every element in the array. So this is my function. So what do I have to do? Well, clearly I have a syntax error here because I haven't given A a type. Let's actually give it a different name to specify that it's a local variable. So multiply every element in this array by 2. Let's step through how we might code this thing up. So if you remember, this line here is equivalent to this line, the address of the 0th element in the array. So these two lines are equivalent. So what type is X going to have to be up here? Int. Why int? The array is ints. And I think we'd agree that a sub 0 is an int, right? But what about the address of a sub 0? Is that still an int? I was like, I can't parse that sentence, man. I don't know what that means. Oh, I think you're on the right track. Hex is a numbering system. Remember, if you have a thing like a sub 0, and you take the address of that thing using the address of operator, remember an address is the exact same thing as a pointer. So by taking the address of a sub 0, we agreed a sub 0 was an int, but by taking the address of it, we are changing this to be a pointer to an int. or put another way, we could do something like this. So everybody think about that. A sub 0 is an int. By taking the address of, we turn it into a pointer to an int. And then I've declared myself a pointer to an int p right here. Does that make sense? Yes, no? So the fact that these two lines are equivalent means that A has to be a pointer to an int. And in fact, A represents a pointer to that first element of the array, the 0th one. So because it's the pointer, if I try to compile this thing, we will probably get something. No? You're not going to give me any warnings at all? It's definitely not right, but maybe this thing just doesn't give the warnings. So this has to be a pointer to an int. I'm going to do this line, which does nothing. I'm just going to put it in there so that we can visualize the execution and see what points where when we get in there. I just wanted a line that I could stop on. So let's see, forward, we've got our array A, we call mul2, and X is a pointer to the first element in the array. So that's good. Of course, we're not multiplying everything by 2 yet, but that's okay. So now the question becomes, how do we multiply all these things by 2? Clearly, X was pointing at the first element, so I could do something like this. Maybe get rid of some of these asterisks. There we go. Dereferences S equals dereferences X times 2. So take the thing that X is pointing at, multiply it by 2, and store it in the thing that X is pointing at. That seems like a good plan. So X points at that, multiply that thing by 2, and sure enough, look at it, change to 20. Great. But then we were done. Then I wanted to change all the elements in the array to multiply them by 2. We multiplied the first one by 2, but not the rest of them. So what should we do? Let's write some kind of loop. Now, as we saw earlier, we have a couple options here. We could use for loops with array notation, or we could use pointer arithmetic to move around. So I kind of like pointer arithmetic. So we're going to have some kind of loop. I'll leave that blank for the moment. And maybe we'll do like we did before. We'll have an x++ at the end of the loop. We just don't know what to put here at these spots yet. But x++ will move us to the next integer. And dereference x equals dereference x times 2. That should be fine. So x will start pointing at the 10. We'll multiply it by 2. Then x++ will point x at the 6. We'll multiply it by 2. Then x++ will point at the 18. We'll multiply that by 2. Plus, then it'll point at the 7, which will multiply by 2, and the 2, which will multiply by 2. And then it's going to point at the address right after that. Yeah. That seems bad. Let me see if I can't run this right now because it's got an infinite loop in it, but I'm going to jump over to the other visualizer and see what this one will do. Oops, function definition not allowed here. What did I do wrong? Void mul2. I'm doing something really obviously wrong, I'm sure. Oh, I didn't close my for loop. There we go. I'm honestly not quite sure what this is going to do. Step. So we call multiply 2. Oh, I didn't turn on that memory thing. Shoot, where's that? Don't have my memory visualizer code in there. I have to put in this magic comment to make this work. There we go. So here's our array of A. You can see 10, 6, 18, 7, and 2 up here at the top of memory. I'm going to jump in here to multiply 2. We have a local variable x that's right here. It's pointing at FFEC, which is the 10. So that's good. So we multiply that by 2. Wow, this isn't working at all like I expected. It's ignoring my x++. I think I've broken this one again. Oh dear. Let's see if we can make this a little happier. I know this is kind of contrived. Ignore these middle bits. I'm just trying to get this to behave like I'm expecting it to. There we go. So I've multiplied the first one by 2. We just multiplied the second one by 2. We move x to point to the next one. We multiply it by 2. So it's working. Look at that. We've multiplied all these by 2. Then where are we? We've stepped off the end of memory, and it's running forever. So this probably would have caused some kind of crash. So what we should really do is figure out when to stop this loop. And this is the condition. And we could try something like this, but we don't have any zeros in this anywhere. It's not null terminated. It's not a string. It's just an array of 5 things. So what could we do? How do we know when to stop this loop? There are a couple options here. Ideas? We could totally pass in a length. Let's do that. Multiply this here, length of 5. Perfect. And now we can do some kind of length thing. Remember, length is a local variable, so we could modify it. Something that might commonly happen is something like that. But we might make this more explicit. We can put this in our for loop. Let's do that. Current equals 0, while the current is less than the length. Here's a little trick. You can actually do multiple things in one of these clauses in a for loop. You just separate them by commas. So what this is saying is, while current is less than length, do the loop and also do these two things. Add one to current, add one to X. This works in JavaScript too, by the way. It's just really rarely used. So I like this one a little bit better. Hopefully that's not an infinite loop. So we step ahead, we jump in. Length is 5, cur is 0. We're multiplying X by 2. Current becomes 1, 2, 3, 4. And then lastly, uses a poo emoji for the pointer that's no longer useful. That's hilarious. So there, we've done it. And now we've dropped out of the loop. And we've totally done it. We've multiplied everything in that array by 2. What if we didn't want to pass in a length? What's another option we might use that we mentioned earlier? Length is totally a valid way to do this, by the way. But as a thought experiment, what if we wanted to make this happen without using the length? What's another option? How do strings do it? Some kind of terminator. We can put a number out here. If we're certain this number doesn't appear in our data set ever, then we could use that to terminate the string. So, or terminate the array. So now I can do something like this, right? This is exactly how strings work, except strings use a null terminator, and here I've made a terminator up. I'm just assuming that 999 is not going to appear in my data set, and if it doesn't, then we should be good. Of course, if for some reason the data set did include a 9999 that I wasn't expecting, now I'm screwed. I'm going to stop processing right here instead of going through the whole thing like I expected. But as long as I'm certain that the data set will not contain my terminator, then I'm good. Oh, no, the array length is 6. Good catch. One of the shortcuts that sometimes C programmers take is if you're using an initializer like this to initialize an array, you can actually leave this blank, and the compiler will be like, looks like there are 6 things, so you meant this. So a lot of times C programmers will take that shortcut for initializing an array. But yes, good catch. The array length became 6. And that is exactly the sort of error that you don't like to make as a C programmer. I'm pretty sure the compiler would have stopped me on that one, though. It would have been like, hey, you said the array was 5, but you gave me an initializer with 6 things in it. What's up with that? But yes, good catch. Any more thoughts on this example? Let me paste this in for everybody. So the compiler generates the \0 if you have a constant string. So for something like this, where we don't have a constant string in double quotes, it doesn't generate it for us. But if you have something like this, the compiler will put that here at the end. So anytime you have a double quoted string, that \0 is implied at the end. It's there. You could always stick another one in the string if you wanted, but now there will be 2 of them at the end. Is that was that your question, Ari? The only case it does that is with constant strings like this. One interesting thing about this is we saw in the other visualizer here that these integers, 20, 12, 36, 14, and 4, these integers on this machine take up 4 bytes. That is, the size of int on this little virtual machine here is 4. Despite that, we were able to jump the pointer from one integer to the next integer by using x++. We didn't have to say x plus equals 4. So when you do pointer arithmetic, this is important, when you do pointer arithmetic like x++, that doesn't just move you to the next byte, it moves you to the next whatever type of pointer it is thing. So because x is a pointer to an int, by saying x++, we're going to the next int in memory. It doesn't matter how big integers are, if they're 4 bytes or 8 bytes, the compiler knows, it figures it out. It's the type of the pointer that dictates how far in memory x++ gets you. And you can always assume that x++ gets you to the next thing, where thing is whatever type the pointer is. It just so happens that with strings, with char arrays, the size of char is 1. So doing x++ with a string gets you to the very next byte in memory. But doing x++ with an int pointer will get you to the next int in memory. That all ties back into how arrays and pointers are equivalent. If you do array notation and you say a sub 0 and a sub 1, you expect to get the next integer with a sub 1. So more questions about this example? Or if not a question, give me an emoji for how much sense this example is making. I don't even know what that emoji is called. That's funny. Anybody else? Somebody must have more emoji thoughts. Don't leave me hanging, guys. I can drink tea all day. I'll open it up, this problem or anything. What is the best way to test the code in C without tests in place? What's the best answer to this question? Well, I'm going to try not to sound like a smartass when I give these answers. So please believe me that I'm not. But one of the best ways is to write your own tests to make sure that the stuff works. If you were like a practitioner of test-driven development, you will have written the tests first and then gone and fixed the code afterwards. But if you're not, then a far more common way is to write the code and then manually run a few tests of your own and make sure that it seems to be working, and then move on. You can definitely use printf to print all kinds of stuff. Like we could put a printf in here that outputted what dereference x was, so outputted what x was pointing at, and then we'd be able to see it go from 10 to 6 to 18 to 7 to 2. So you can totally use printf to do something like that. I don't think this visualizer doesn't have output on it, but this one does. What do we have here? Let's switch it to the, edit, hang on a second. Let's switch it to our 999 terminating version, and I'm going to leave this crazy x equals x thing in here because I think it's making this interpreter happy to have that in there. I was going to add a printf, huh? But we might want to see what's there. So we could do something like this, before and then after, something like that. If we were interested in what the pointer value actually was, like the address itself, we could put that in there. So we'll print out not only the pointer value, the address is pointing to, but also what's at that address. So this could be like printf debugging. See, it's warning me. Access elements in the initializer. I forgot to set this to 6. So here's stepping through. Now we get some output. So before, the pointer is pointing at FFE8 and the value is 10. Afterwards, the pointer is still pointing to FFE8 and the value is 20. We go to the next one and we see that it's moved to the next pointer position. We've got 6 and 12 and so on. So something like that, Michelle. All right, request from Malloc and Structs. I'll do Malloc and Structs, and let's do that in a few minutes. I want to do a quick exercise before we do that. And this is an exercise about types, something that my C instructor did for me way back in 1930 that I thought was kind of useful. So I'm going to ask some questions about types, what type data is. And so I'm going to write some types here, like int a, and then I'm going to ask what the type of this expression is, such as a. What is the type of that expression in C? And here, the type is int. We've declared a to be an int, so the type of the whole expression is an int. Likewise, this is a float, and this is a char. So So that's the warm-up. So here's a question. What type is S? Just shout them out. Char pointer string is a reference. It's a string. Yeah, both of these are correct. But I'm going to use the C type. I'm going to say that this is a char pointer. But this is also known as a string. Pointer to a char, also known as that. So yeah, that's the type. What about the type of this expression? The address of C, we could say. What's another word for address and location? Pointer. And what type is C? Pointer to char. Yeah, that's what we got here. I'm going to put the C type in for that. So we had C, which we agreed was type char, but then address of C, that's type char pointer. So here's an example of using the address of operator to get a pointer to a thing, and see how it changes the type of the expression there. And expressions changing types with operators isn't that uncommon. And C, if you've got something like this, two, this is actually a valid line of C, by the way. You could just write 2 semicolon, and it'll compile. It doesn't do anything. It's like, it'll tell you, it'll warn you, it'll be like, you've got an expression here, 2, it does nothing, but it'll actually compile. So what type is this? What type is this expression? It's an int. What about this? It's float. What about this expression? What type is that result? It could be a double, but let's just say float for now. The result of the whole expression is a float. Yeah, interestingly. So even though this expression has an operator in it, a plus, and this has an int at the beginning, the result of the entire expression has a type, just like the result of the entire expression address of C has a type of char pointer. All right, let's do some of the reverse stuff. So we already agreed that S was a pointer to char. What about this? Char, the value of S. Yes, both of these are right. Well, I'm going to say the value that S points to. So here, if I cut this out and put it down here, you can see how these things are sort of inverses. We have a char, we want to go to a char pointer, use the address of. We've got a char pointer, we want to get the thing that it points to, use dereference. What about this? If you dereference the pointer, you get the value. Jonathan, but I feel like I might be missing your question. Okay, cool. Yeah, so in this guy, this is the same as dereference S, and we decided the type of dereference S was char, right? So there we go, because these two things are equivalent, just like as if we typed this. This is also a char. What about this? Int pointer. Value that A points to. Yeah, so normally this would be the value that A points to, but what type is A? A is just an int. A isn't a pointer at all. This is an error, in fact. You can't dereference a thing that's not a pointer. It doesn't make any sense because it's not pointing to anything. It's just an integer. All right, one more before we do structs and stuff. We already agreed that S is a char pointer. What about this? Learning, sweet. Yep, I'll paste it in. Still a char pointer. That's a good guess. But it's actually something different. You can think of it this way. Back up here in this example, we had our char, we put an ampersand on the front, it added an asterisk. Yes, this is the same as the address of S. So this is where it gets funky. This is also a pointer to S, right? We agreed up here that address of S, location of S, pointer to S, these are all the same thing. This is a pointer to a pointer. The type here is actually char pointer pointer. We call this one level of indirection and this 2 levels of indirection. So every time you take the address, you're basically adding another asterisk on. You're adding another level of indirection. So the main use of that is when you want to change a pointer inside a function. Just like if you want to change the value of an integer inside a function and have that change reflected out in the caller, you have to pass a pointer to that integer. And then you can change what the pointer points at, and then back in the calling function, they see the result. If you want to change the memory address that a pointer is pointing to inside a function, then you have to pass a pointer to that in. And there's an example of that in this function. String to unsigned long. This is a function that's hello, mouse? Wake up. There we go. String to unsigned long is a function that converts a string that has a number in it. Like maybe you typed in a string on a number on the keyboard, and you want to convert that into a variable value. One thing that this function can do is it can tell you the first invalid character. Let's say I ask it to convert the number 1 to p into an integer number. It would be like, hey, you put a letter P in there, and that doesn't mean anything to me. So I'm going to tell you where the first bad character was. And so it actually takes a pointer to a pointer right here. You can ignore the word restrict. It takes a pointer to a pointer. and you pass a pointer to a pointer in, and it'll change what that pointer points to. And then you'll see that change resulted out there in main. It's exactly analogous to passing an int into a function versus passing a pointer to an int into a function. It's just we've got more levels of indirection. But I don't want to run a demo of that today. I can do that tomorrow because I do want to throw in some stuff about structs and Malloc. But we can totally put that on the agenda for tomorrow. Another place you see it is allocating dynamic multi-dimensional arrays. So right now we'll do some demos where we allocate one-dimensional arrays, but if you allocate a two-dimensional array, then pointers to pointers are there. If you allocate a three-dimensional array, pointers to pointers to pointers, and so on. But they don't appear very commonly, thankfully. Two levels of indirection like char pointer pointer, kind of rare. Three levels of indirection, char pointer pointer pointer, that's really, really rare. So here, let's throw this snippet in here. Every expression in C, every one of them has a type associated with it. When you call printf, that line, printf hello world, that has a type. It happens to be the return value of printf, which is an int. So let's see, should we do some Malloc stuff? Malloc or struct? Let's do both. Let's do structs. I'm going to make a struct up here. So the idea with the struct is that we have a bunch of related data that we want to bundle it together into a single variable. This is exactly like an object in JavaScript or like a in iOS. Somebody help me out. In Swift, what do? It's a class, an object? Is that what you have when you want to bundle a whole bunch of data together into a... I just want to make sure I'm using the right terminology. Some languages like Go and Rust still call them structs. Classes and structs. C++ also has classes and structs. So a struct is very much like an object or a class, except it typically doesn't have any methods on it. It's typically just data. You can kind of fake it with pointers to functions, but usually structs in C just have data in them and no methods or functions associated with them. So I can make up a struct like this. This doesn't actually make anything. This is kind of like declaring a class. And we haven't really instantiated anything, even though that's a word that's not really used in C very much. But I can add some stuff to it. Oops, semicolons go here. So this defines what a struct animal is, but we haven't actually made any of them yet. It's important to note that this is the type. So like we were saying, 2 is int. The name of the type is int. The name of this entire type is struct animal. It's 2 words. The type has 2 words in it. Struct animal is the type. And you can declare variables of that type. So there I've declared a variable, struct animal, just as if I declared an integer a. A hasn't been initialized. Neither has x. But I have one of them now. And I can initialize x like this. So this is probably syntax that looks pretty familiar. Languages that use this syntax got it from C. So here we are. And I can print these things out. We'll leave that blank for now, x.name. And same thing for x.leg count. What should I put here? Percent what? For x.name. You can ask yourself, what type is this? Just like we did that previous exercise. X.name, the type is, yeah, the type's char pointer. So we want %s because it's a string. And then for leg count, do %d for int. All right. So here's an example of declaring a struct. Again, this doesn't actually allocate any space or anything. It just tells the compiler what this type is. And then later on, when we declared one, that actually got us some space for one. It was uninitialized, so we initialized it. So this is a great question, Carlos. If we use %c, would we get G for goat? Well, let's look at the types here. %c wants to print out a char. And what type is x.name? X.name is a string, also known as char pointer. So we've got kind of a mismatch here. %c wants a char, but we gave it a char pointer. How could we take our char pointer? How could we get a char out of it? Or put another way, well, if we put %p, it would just print out the big number that the pointer value is. But I want to print out the letter G for goat. Put another way, x.name points at the string goat because it's a char pointer. It points at the G. How do we go from the thing that it's pointing to, or sorry, the address that it's pointing to the thing at that address? That totally works, Carlos. X.name sub 0. That totally works. Give us the first character in the string. So we could do that, and that'll work, because here the types match up. What we want, what we have. Of course, by the pointer equivalency thing, this is equal to dereference x name plus 0, which is also a char, and that is equivalent to dereference x.name, which is also a char. And I'm trying to remember the operator precedence here. I don't remember if I need to have parentheses around that or not. The question is, does the dereference happen first, which would be bad? Or does the dereference happen second, which would be fine? I can't remember. I'd have to look up operator precedence. So yeah, you can print it out this way. But, so that's pretty straightforward. One of the weird things that often happens is we'll have a function that takes a pointer to that type, struct animal pointer A, we'll say, and does something with it. Let's say we wanted to print out this thing. It's called print. So I want a pointer to my struct animal, so I'm going to give it a pointer to it. This doesn't actually compile anymore. And so this might trip people up. You see that we use dot notation right here. And that was fine because X was a struct animal. But if it's a pointer to something, dot doesn't work anymore. It doesn't work on pointers. So we have to, oops, sorry, A. So we have to this was a pointer to animal, but we need it to be an animal. So how do we go from pointer to something to the thing? So we have a pointer to a struct animal, but I just want the thing that that pointer points at. Dereference it. So we can dereference this like so. And now we're good. Because you can use the dot operator with the struct animal, and we've dereferenced the pointer to turn it back into the struct animal that it points at. So that's good. But this is unwieldy syntax. So there's shorthand. The arrow operator. These are the same thing. So the general rule is if you have a pointer to a struct, use the arrow operator to get at the fields. If you have just a regular struct that's not a pointer, use the dot operator to get at the fields. Let me drop that in there too. All right, I've got 2 minutes left, so I want to do a thing with Malloc, and it's just going to be something to leave you with. But if you have more questions about it, Help Channel is always here, of course. If I declare this to be a pointer, that's fine. We can switch these to be this, and now we already have a pointer. X is already a pointer to a struct animal, so we don't have to take the address of it anymore. So this kind of works, except we haven't actually allocated any space for it. When you declare an integer like this, you get space for an integer. You can store things in it, like 12. But if you declare an integer like this, you don't get space for any integer. You have to assign p to point to something before you could use it. Then you could do things like this. But p doesn't point to anything right now. It just points to garbage. Likewise, struct animal pointer x doesn't point to anything, so we can't assign things into it yet. Just like if we did this, we'd get a crash because p is pointing somewhere in memory that we don't have space for anything at. So we need to initialize x to something, and you can do that with this function, malloc. So this will give us space for one struct animal. So this will allocate that memory. We tell it how many bytes we want to allocate. We use size of to figure out how many bytes struct animal is. And now we're golden. We've got that space allocated. This space will stay allocated until we free it or until the program exits. So I'm going to explicitly free it down here. So this is a quick, dirty demo of how malloc works. You can malloc bytes for anything you want. I could malloc space for an int right here if I wanted to. But here I'm mallocing space for this struct animal. Then I can use that space. So this gives us a way at runtime to allocate space for things. And this is really useful, like if you have a linked list or something, where you don't know how big it is at compile time. And at runtime, you want to add more nodes onto that linked list. When somebody wants to add a node on, you malloc space for that new node, you fill up that new node with whatever structure you need, and then you attach it to the linked list. So that's as far as I want to go on this because I'm out of time. But any last minute questions? For today, just plowing ahead on that repo. Tomorrow we'll switch to processes and system calls, which is arguably, in my opinion, easier than wrapping one's head around syntax. It's more of using C than learning C. So point out that lots of code shows a cast right here. You might see code that has something like this before malloc to force the type of malloc to be struct animal pointer. Historically, this was necessary. It is no longer necessary. So you might see that out there, but you don't need it. Last minute anything? I'll post this code as well. Last chance, last minute thoughts before hacking? I didn't actually compile any of this stuff, so sorry if it has errors in it. All right. I'm going to stress one more time that pointers are hard. So if you're feeling like they're kicking your butt, then believe me, you are in good company. Generations and generations of programmers have gone through the exact same thing. But I know you can figure it out. It's just a matter of practice. The more of it you do, the more sense it makes, better at it you get. Pretty soon you'll be writing functions that dynamically allocate four-dimensional arrays using quadruple indirection, and it'll be fine. All right, gang. Keep the questions coming. All these questions that you guys have asked, like on the help channel and in here, these are all awesome, awesome questions. So keep hacking at it. If it were easy, it wouldn't pay well. Remember that. And you will get it. I guarantee it. All right, gang. Catch y'all later. Enjoy your lunch.